Okay, y'all. So we're going to pick up on the notes where you're just going to be given a function. And we're going to do what they call the 4-step process of analyzing the function, analyzing the first derivative, analyzing the second derivative, and then sketching a graph by hand, but only for polynomial functions. So what that means is you're going to be able to use some algebra knowledge to kind of check if your graph is making sense. So let's take a look at this 4-step process. I'm just going to talk you through it, but I put it up there for reference when you're doing your notes, because we need the whole page to do this 4-step process. Okay, so here is our function. It's polynomial, it's degree 4. So already in your mind, you might know, like have a sense or an idea of what this function might look like. So I'm going to be quiet for a second. Just draw like a general random shape. Well, not random, but a general shape of what you think this might look like, just based on your algebra knowledge. Okay, so hopefully just based on your algebra knowledge, you know if it's degree 2, which is not, that would be a parabola, right? And if it's degree 3, that's when you have a cubic function that looks kind of like that. This one's degree 4, so from algebra knowledge, you might remember that it's going to look maybe either something like this or something like this. So it's an even function. It's an even function. On even functions, the ends point the same direction. Oops, I forgot the little 4 there. So it's an even function, so those ends are pointing the same direction. And I know it's going to open up because my leading coefficient, this leading coefficient right here, was +1. So the ends are going to point up. So you kind of have an idea of what this graph is going to look like, but you have to do a more detailed graph than that. We're going to point out important points that we need to include on our graph to get full credit. So here we go. Oh, okay, so step number 1. And on the test, I'll have step number 1 be A, and I'll tell you what to do. And step number 2 be part B, and I'll tell you what to do. But on my math lab, it's just going to say graph it, right? So make sure you're practicing all the steps because I'm going to assign points for each of these steps. So step 1 is where we analyze the function. You're going to analyze f of x. And you have to pick out 2 important points. Okay, the important points you need to pick out are the x-intercepts and the y-intercepts. You would also want to state the domain of the function, but since you're only going to be asked to graph a polynomial function, the domain will always be all real numbers. So you don't have to worry about that so much. But you do need to find these x-intercepts and y-intercepts. So this is algebra. So x and y-intercepts both involve a 0, but one time the 0 is going to be the input, and one time the 0 is going to be the output. So without getting too technical, let's just plug in x equals 0, because that's the easiest thing to do. And then we'll talk about which intercept that is, right? So the first thing we're going to do is plug in x equals 0. So that means you're putting 0 into the function, and you want to see what comes out. That's the easiest calculation. So let's do that. Let's just put 0 in there. So input to the 4th minus 4 input cubed. 0 to the 4th minus 4 times 0 cubed. That's just going to give us an output of 0. So I take that information, that input and output, and I create an ordered pair, 0, 0. Well, that happens to be the origin of the graph. The origin of the graph is simultaneously an x-intercept and a y-intercept, right? Because it's where both axes intersect each other. So it's both an x-intercept and a y-intercept. So I'm going to put that on both of these. 0, 0. Okay. Now, the harder thing to do algebraically is to figure out what x value or values can I plug in to make the function output a 0. Inputting a 0 is easy. Outputting a 0 usually involves a little bit more algebra. So I'm just going to take my function. My function rule was x to the fourth minus 4x cubed, and I'm going to set that equal to 0 and ask myself what inputs would make that happen. So you might have to do some factoring. We can't use quadratic formula for this because it's not quadratic, but we can factor. There's a GCF. Remember, the first step of any factoring question is there a factoring problem is find the GCF. So here the GCF is x cubed. So I'm going to factor that out. I'll label this as my GCF. And if I factor an x cubed out of the first group, that'll leave me with 1x remaining. And if I factor the x cubed out of the second term there, that just leave me with a minus 4. Okay, and then once you factor it out, you just do your zero product principle. So either the first factor, either x cubed equals 0, or the second factor, x minus 4 is equal to 0. I know x cubed can be really intimidating, but if you cube a number and you get a 0 out, remember it's repeated multiplication. The only way multiplication can equal to 0 is if you multiply by 0, right? So this one, you could take the cube root of each side if you wanted to, but then the cube root of 0 would just be a 0. I heard a little chimes. Give me a sec. Mind blown with that one. Okay, so let's hop back over here. And then if x minus 4 is going to be a 0, the only way x minus 4 can be 0 is if x is a 0, right? So we need to translate those into ordered pairs. So this first 0 saying if the input x is 0, then I'm forcing an output of 0 in my function. And we already found that one earlier. And the other ordered pair is if I input a 4 into the function, I'm going to output a 0. And if you think about sketching that on a graph, 4, 0, 1, 2, 3, 4 on the x, 0 on the y, see how that's an x-intercept? So even if you didn't remember which was which, once you figure it out, you could be like, oh, that's an x-intercept. So I'm going to label it up here with my x-intercepts. So all of this is algebra. Step 1 is just straight up algebra. Technically finding your domain, but for a polynomial, it's all real numbers, and finding the x and y intercepts. And you just do that by one time you figure out, you make x your input, and one time you make x the output. Oh, sorry, you make 0 the output. So one time we're going to do a 0 input, and one time we'll do a 0 output. So show me a status. How do you feel on step 1? Got a couple happy faces. Okay. Dusting off some cobwebs. Step 1 is always the same for every function. It doesn't matter if it's a polynomial. It doesn't matter if it's rational, whatever. This is step 1. Yes, for step 1, you're always using 0, either inputting a 0 and finding the related output, or setting the output equal to 0 and finding the related input. Always, always for step 1. Okay, so step 2. Step 2 is now we need to analyze the first derivative. So let me come over here and shrink this down. And I'm going to erase that graph because we're not ready to graph yet. Need some more info. It's pretty small, but here we go. So I'll erase that. Okay, so here we go. Step 2, analyze the first derivative. Can you see why I left us a whole page for this? Step 2, analyze the first derivative. And basically what that means is to create a first derivative sign chart. So on your test or on your quiz, I'd label part B, create a first derivative sign chart. So you don't have to memorize the steps, but let's go ahead and do that. So we know our original function. Okay, and just find the derivative. It's just power rule. Remember your input here. X is the input, is a variable, an input variable. So if you don't have to do the chain rule because x prime would just be a 1. So the derivatives on test 2 are pretty complicated, but on test 3, x is always going to be your input variable. So the derivative will always be a 1, so you don't need to do the chain rule. Okay, so when I take my derivative here, it's just basic power rule. Just drop that down. That'd be 4x cubed increase the exponent by 1, and then drop the 3 down. That's minus 12x squared. Okay. And then when you create your sign chart, you need those partition numbers. The partition numbers occur when either the derivative is 0 or it's undefined. Either the derivative is 0 or it's undefined. Polynomials are always defined because it's, domain is all real numbers. There's no holes or jumps or asymptotes or anything. So all I need to do to find my partition numbers is to set the derivative equal to 0. So I'm just going to set f prime of x, this thing I just got, equal to 0 and figure out what x values make that happen. Okay, so again, we're going to have to factor here. So my GCF is a 4x squared on this one. If I factor out a 4x squared from this group, I'll just be left with an x minus factor out a 4x squared from this group. That'll just be a 3. And set those factors equal to 0. Okay. You're probably able to see that the only way 4x squared can be 0 is if x squared equals 0. Technically, 4 is its own factor, but 4 can never be 0, right? So 4 doesn't really come into play. And the only way x squared can be 0 is if x is a 0. So that's one of our partition numbers on our number line. And again, over here, the only way x minus 3 can be 0 if x is a 3. So I'm going to take those numbers and partition up my first derivative sign chart. Okay, and then it's a little tedious, y'all, but you got to do those test points. So we're just going to test an x value in each of these regions. So maybe let's test x equals -1. Let's test x equals +1. And let's test x equals 4. So these test points, we don't draw them on the number line. You only put the partition numbers on the number line. The test points, remember, are telling us whether the outputs of, in this case, the first derivative are positive or negative. So let's go ahead and do that. So we're plugging these into the first derivative. Oops, thought that was my highlighter. We're plugging these into the first derivative, into this rule right here. Okay, so let's go ahead and do that. So that would be -4 minus 12. So -16. So all I care is that this is a negative output. That's all I care about. So I'm just going to come over here and put negatives up there. And you could type all of this expression into your calculator if it's programmed to do order of operations and jump straight down there. I don't have my calculator handy, so I just did it in pieces. Okay, so my first test point area is going to be negative. Let's do our second test point here. Let's do +1. Okay, so that gave me 4 minus 12, so still a negative? Can anyone confirm that one, that that's still a negative there? Yeah, okay, cool. And it's okay. We'll interpret that later. Right now we're just creating the sign chart. And then let's plug in our last test point of a 4 here. Okay, I have no idea what that is, but I can tell it's going to be positive because 4 cubed and 4 squared. But let me grab my calculator real quick. Ooh, positive 64. That's super positive. But all I care about is that that's a positive value, so then I'll put pluses on here. Okay, so show me a status, since I can't see your face. Show me a status on how you're feeling about this first derivative sign chart. How are you feeling about step 2? Finding the partition numbers, testing points in the intervals between the partition numbers. Later, we're going to use this to graph slopes of tangent lines. Right now, we're just creating that. Okay, so let's go ahead and do our step 3. Step 3, we're just going to create a sign chart for the second derivative. So let me shrink this up. I'm going to have to make another. I should have given us 2 pages. Just so you know, there'll only be one of these on the test because see how long they take. So I'm just going to add a page real quick here because there's no way I'm going to fit all that on there. These are so fun for me to grade. It's not insert new pages. Oops, 1. Let me try that again. Insert new pages. 1. Okay. So now let's do I'm just on the new page. I'm going to do the second derivative, but I'm going to start writing here so I can see what my first derivative was. Okay. So step 3, y'all, we need to analyze the second derivative. Oops. So that just means you're going to create a second derivative sign chart. So I'm going to go ahead and record my first derivative here before I move my page up. It was 4x cubed minus 12x squared. Okay. So let's go ahead and do our second derivative and create a sign chart. Again, just power rule. That would be 12x squared. Minus, and then 24x. Technically to the first, but don't write that. Cool. Yeah, and then we just find our partition numbers. Again, it's a polynomial, so all we need to do is set the second derivative equal to 0. It's kind of repetitive, right? Way better than doing a log function or a rational function, though. I'd much rather it be repetitive. Okay, so let's just factor out that GCF. It's going to be a 12x in this case. So that would leave me with an x minus 2. Okay, so either this 12x is equal to 0. Well, technically just the x, right? Because 12 is its own factor, but it's never going to be a 0. So one partition number is a 0, and the other partition number will be a 2. So let's put those on our sign chart. And make sure, y'all, on your test that you're labeling the sign chart very clearly as the second derivative sign chart. So label it F double prime. Because what's going to happen, see how long this problem is? I will grade for partial credit. So if you mess up step 2, if you find the wrong first derivative, I'll use your wrong first derivative to find the second derivative and rework all the problem. It takes me forever to grade, but I will do that. But only if you're labeling everything really clearly. So I don't have to fish around too much, right? So I labeled this one second derivative and its partition numbers are 0 and 2. And the second derivative was 0 at both of those points. So just do your test numbers real quick. I'll be quiet while y'all do your test numbers. Oh, before I'm totally quiet, just make sure you're plugging them into the second derivative to test this time because it's a second derivative sign chart. Can anyone confirm my sign chart? At least the signs, are the signs correct? Cool, thank you. I know it's tedious. I know, like, finding all these numbers, but make sure you're showing this work that I put down here. So if you do make a little mistake on your test, I can give you lots of partial credit. So at least show me that you knew to take the test number and plug it into the second derivative. At least show me that, so I can give you partial credit, because it's so easy to mess up. Like, look how many chances you have to make a silly typo in the calculator or a silly righto on your test, right? So be super organized and just write it all out. Okay, before we put all these steps together to sketch a graph in step 4, are there any questions or comments? Okay, we're going to put all this together. Let me shrink this up a little bit. If any of y'all have a touch screen that you can write on with a stylus, I'm using the Drawboard app, and they have a really awesome free version now. I hear I got this one a long time ago when it wasn't free, but just so you know, it's kind of fun to shrink your work. That's nice. But anywho, okay, so step 4, we got to put all this together. All of this together. We got to put our information from step 1, our information from step 2, and our information from step 3 on a graph. And I am spread out all over the place. So I'm going to come copy this sign chart real quick and move it down here so I can see it better. So let's duplicate that. Okay, so I'm going to take this information, okay, and then I need our x-intercepts and stuff from the first one. I remember the 0, 0, so let me go find that up there. Oops. Uh-oh. My app did not like that. It's stuck. No one panic. Here I'm just saying, you should get the Drawboard app. It's free now. It's stuck. Okay, well, let me see if it'll let me change pages. Let me pause the video. So how are we feeling on putting all those steps together and graphing in step 4? Show me a status, ask a question. Think back to your prediction when you just saw that function for the very first time, when you saw it was degree 4 with a positive leading coefficient. Did our calculus match what our algebra prediction said? Yeah. The ends are pointing the same direction. They're both pointing up. It's kind of squiggly in the middle. Okay, so your algebra can kind of reinforce this, but I have to see all the calculus. And you'll have lots of practice on your homework, but we're not going to do another example in class, because see how long they take? They take forever, and we have lots of other stuff to do. Okay, and since I wasn't recording during that time, I'll post an old video from the last time I taught this course online, but I will, it's going to be a different function, but at least you'll have another example of this process, okay? Cool. We're recording now, though. Okay, so we have another, this is the problem we kind of started last class when I thought we'd have time to finish it, and we didn't. So let's just start it from scratch. Okay, here we go. Wait, before we do this, I'm going to pause for 10 seconds, and I want you to get up and stretch. Maybe jog in place for 10 seconds. You're going to need some brain power for this, okay? Crack your knuckles. Move your head around, whatever you need to do to get blood to the brain. Okay, are you ready? Because you're going to need some brain power. Here we go. Okay. So the derivative of a given function is graphed below. I'm going to highlight that. The derivative of the function is graphed below. Underline, underline, derivative. Derivative. See how this is labeled f prime of x? And last class we talked about knowing the shape of the graph is quadratic. I know that the f prime function is quadratic because when I graphed the derivative, it's U-shaped. But we're being asked to sketch a possible graph of the original function. So if I know the derivative is quadratic, if we kind of think backwards with power rule, if when you do the power rule on the original function, it decreases the degree by 1, then if we think backwards, if I know the derivative, I can go back to the original by increasing the degree by 1. So I know my original graph should be cubic. I just don't know quite the shape, but since it's odd, you know, the end should point in opposite directions. I'm not quite sure which of these shapes it should be yet. But at least we'll know if we're on the right track when we finally graph the original function. It should be a cubic function. Okay, how in the world are we going to do that? Let's see. So what we're going to do is we're going to create a first derivative sign chart. We're going to use the graph to make a first derivative sign chart, and we're going to create a second derivative sign chart. And you've got, this is where our brains have to turn on. So let's do this. Let's create the first derivative sign chart. So I'm actually going to shrink this real quick. Move it over here. Okay, here we go. So we are going to make a first derivative sign chart. And there's a super duper tempting point to put on here. So I'm expecting people to get this wrong. But if you get this wrong, it's because it makes sense in your head. And I have to convince you it doesn't make sense for you to not make the mistake again. So if just looking at this graph, what does your brain think the partition number should be? What do you think? Just looking at this graph, what do you think the partition number should be? Remember, partition numbers are where the first derivative equals 0. Is anyone tempted to say this point right here? Yeah. Isn't it super duper tempting to say that? It's so tempting, right? So if you were thinking that, this is where you have to convince yourself why that did not make sense. Oh, go ahead. Oh, I thought I heard a hand, but I don't see a hand. Never mind. Okay. So we have to convince ourselves why we're not going to put -1 on this chart. So here we go. The reason why is because this graph is of the derivative, right? It's of the derivative. So the outputs of this graph, describe the first derivative. Outputs of the f prime graph describe the first derivative because this is the graph of the first derivative. So this point right here, we're really putting -1 into the derivative and the output is down at -2. Because I'm just reading points off the graph, right? It's a graph of the derivative. If I read points off, that's inputs and outputs for the thing being graphed. The derivative is the thing being graphed. And that's not a partition number. Our partition numbers are where the derivative is equal to 0, right? So let's actually think about what is the derivative of that. Y'all, if I did a tangent line here, there is a horizontal tangent line, but the tangent line describes the derivative of this. So tangent lines to a first derivative graph describe the second derivative, right? If tangent lines are derivatives, and this is the first derivative graph, then I know the derivative of this derivative at -1 is 0. The second derivative is going to be 0. So actually, if we go to create a second derivative sign chart in a minute, -1 is going to go on there because if I put -1 into the second derivative to the tangent lines of this graph, the slope at that point is 0, and the slope is the derivative of what was graphed. I know that's a lot. Does anyone have any burning questions before I continue? Because if you're still not sure, maybe when I go on, it'll help. But any burning questions right now? Probably don't even know what to ask yet, but that's okay. So let's keep reading this. So where would the first derivative be 0? So look at the outputs of the graph. Anywhere on this x-axis, this is my x-axis, right? Anywhere on that x-axis where the output is 0. So what inputs create an output of 0? So that's going to be this point right here. When I put that input, -3, into the graph, which is prime, then an output of 0 comes out. So -3 is going to be a partition number on the sign chart. And same thing here. If I input a 1 into the thing being graphed, and the thing being graphed is the first derivative, the height of the graph is 0. So that's my other partition number. So I have my partition numbers. Now, remember, we're still thinking about outputs. Let's just do some test numbers here. Let's test -4. I don't know, maybe 0. 0 is usually easy. Let's test 2. And all I care about are the outputs positive or negative. That's all I'm caring about. If I put -4 into the derivative, because I'm creating a first derivative sign chart, so I'm going to put -4 into the derivative. Let's go look on the graph and see what that would be. So here's -4 on my graph. I put it into the derivative, which is on the graph, and see how I get +2 out there? If I put -4 into my graphed derivative, I get a +2. And all I care is that it's positive, so I'm just going to put positives out there. So basically, instead of putting the test point into a derivative function, I just read the test point off the graph because the graph is the derivative. Let's do the same thing with 0 here. If I put 0 into the derivative, ooh, this one's a little harder to read because it's not at a pretty point. Here's my input 0, and it looks like, I don't know, -1.3 or something. I don't really care about the number. I just care that that's negative. And then when x equals 2, if I input a 2 into the derivative is graphed for me, so I just read the graph up here. It comes out to be a +2, and again, all I care is that it's positive. And that these are zeros. So I'm going to put a little note there. We need to, let me put this in words. So when you look at this later, you're like, what in the world did she do? In words, I'm going to say this. I'm going to say, since the graph shows f prime of x, we just read the graph. We just read the points on the graph. Just read the points on the graph. To get info about f prime. Okay, I'm not even gonna, well, I should. I'm gonna ask for a status, and it's okay if you put a frowny face or an I have no idea what just happened face. Go ahead and give me a status. I'm scared. Shocked face. Got one happy, got another shocked. Got a couple confused. Okay, no one put a frowny face yet. You know, I appreciate the positive attitudes. And just as a reminder, the real learning does not happen in class, right? We lay a foundation. We try to get vocab and basic examples down, but you can't learn calculus in an hour, 20 minutes twice a week, right? You have to do lots of work outside of class. So make sure you're reaching out because I know this stuff is tricky. Okay, let's get our second derivative sign chart. Okay, so let me write this out. Since the graph shows f prime of x, and tangent lines are the derivative of the graph. And tangent lines show derivative of graph. Derivatives. We read the tangent lines of the graph to find f double prime, right? Because the derivative of the graph is the second derivative. So we read the tangent lines on the graph. To get info about second derivative. We read the tangent lines of the graph to get information about the derivative of the first derivative, which is the second derivative, right? So let's come up here and read tangent lines. So if I just pick a test point, we know at -1, the tangent line went horizontal, right? So there's a horizontal tangent line here. At x equals -1. So let's test a point here. Let's test, trying to pick a pretty one. Let's test -4. Let's find -4 on the graph and just look at its tangent line. So here's the point on the first derivative graph where x equals -4. So if I put -4 into the second derivative, I'm reading the tangent line at that point. The tangent line is going down. I don't know the exact number. I mean, I could find the slope there. I don't want to. I don't know the exact number, but I know it's pointing down. That means it's a negative. So all of these are going to be negative. And then same thing on the other side. I don't know. Let's pick a test point of, say, 2. If I put 2 into the second derivative, I'm reading the tangent line at that point. So when I come locate x equals 2 right here. Oh, wait, that's 1. X equals 2 would be this point up here. See how my tangent line is pointing up there? I don't know what it is exactly, but it's pointing up. That means my tangent lines will all be positive in that region. Down here, my tangent line went horizontal, so put that in green just to mark it there. So we were given the derivative graph, so we took information directly off the graph to make the first derivative sign chart. To make the second derivative sign chart, we know that's the derivative of the derivative. That's the tangent lines of the derivative. So I took the tangent line information and put it on the second derivative graph. And now we're going to use those sign charts to sketch a possible graph of the original. A possible graph means there's more than one right answer. Just a possible. So what I'm going to do, you should always be scared when I give us a whole page for a problem, right? So I'm going to relocate these sign charts down here just because it's hard for me to scroll and see everything at once. Hopefully my app doesn't freak out on us again. Okay. And this is my advice to you. Are you ready? So my advice is, we looked at the original graph and we knew our original function should be cubic, right? So I'm going to say f prime of x should be cubic. But once you get that piece of information, completely ignore the graph that was given to you. Do not even look at it. It'll confuse you. Don't look at it. I need to exit out 20 mil. Don't look at that. Don't look. You know you're going to look on the test, guys. Don't look at it. Only use the sign charts. So only, let me get all those lines off that I did. Maybe I was a little overzealous. I just want you to overemphasize. Do not look at the original. Don't do it. Okay. Once you figure out it should be cubic, then only use sign charts to graph the original function. Only use the sign charts. Okay, so what information do we get off of our sign chart here? So from the first derivative about the original graph, that's going to tell us local extrema of the original graph. And the second derivative sign chart is going to tell us concavity of the original graph. So we just got to put all that on a graph. And it's possible you're not going to know exactly where to locate things, but as long as your graph has the basic shape and the correct local extrema, well, the local extrema is in the correct X location, you'll be fine. How high you put the local extrema, I don't know. How low you put it, that's why it's a possible graph. Where you locate them, that's just where it's possible. Oops. Okay. That is not the notes. Wow, this is even too much for the app. It's a really big file because I've done so much writing on it. Maybe that's, oh, okay, well. Here we go. Okay. So let's put it on here. So let's go find our local extrema. So my tangent lines of the original graph are going to go up. They're going to hit 0 and they're going to go down. So I know I need a local max when x equals -3. Then my tangent lines are going down. They're going to hit 0 and they're going to go back up. So I know I need a local min here. Okay, so let's go locate those. We don't know exactly where it is, so I don't know. But we know they're going to happen at these points. So the local max, let's kind of over-exaggerate it and put it up here. And the local min, I mean, we're just possible graphs, so we're just going to put it down there. And I'm just going to label those. This is going to be a possible local max. The thing you have to have correct is that it's happening when x equals -3. How high you put it, that's what makes it a possible graph. And for the local min, you have to have it where x equals 1, but how low you put it, that's optional. So that's our local min. Okay, and then we have an inflection point here. So let's graph that inflection point. Because see how it's changing from concave down to concave up? So that's an inflection point at -1. So again, you don't know exactly where to locate that, but it has to be somewhere along this input line, right? And it has to be between the other 2 points. So I don't know. Let's put it here. I could have put it anywhere along that orange line. Well, let me make that orange line the correct. Anywhere from here to here. I guess not all the way to the maximum, right? So anywhere in this orange region, I could have put that inflection point anywhere in there. And then I just need to connect it and we'll end up with a cubic looking function. So I'm just going to go concave down until I hit the inflection point. So all of this needs to be concave down. I hit my inflection point. Then all this needs to be concave up. So as long as your graph is in that shape and your inputs are lined up correctly, that is a possible graph of the original. And you can test it with your tangent lines. You can say, okay, were my tangent lines going up till I hit 0? Yep. Then were they going down till my tangent lines hit 0 again? Yep. And then were they going up? Yep, it follows my sign chart. Okay. How are you feeling? Honest status check. How are you feeling about it completely ignoring the first graph that was giving us? So just putting that information from the sign charts onto the graph. How are you feeling about that? Just transferring information from sign charts to graphs. And just know you will have a question like this on the test. If you mess up your sign charts, but whatever you create, whatever graph you construct matches your sign charts, I'll give you partial credit. So make sure you're labeling things really well. You'll lose some points for not making the sign charts correct, but you'll get points for transferring that information from the sign charts to the original graph. And I'm going to tell you something right now, just to kind of give you a heads up. The biggest mistake I see, and I've taught this class for 10 years, the biggest mistake I see is this, that students accidentally read this original graph as f of x, and then they create these sign charts, right? And then they create their graph, and guess what? They recreate the exact same graph that was given to them. If you do that, you messed up, right? They do all this work, but they didn't realize that the derivative was graph. They just thought that was the original function, and they used that information to create the first and second derivative sign chart, and they plot it. Of course, you're going to get the original graph back, right? So if that happens, you know you messed up. Oh, I think I heard a chime, so let me come back over there. Oops. Yes, that is correct, Cassandra. Since that's why in the question it says to sketch a possible graph. So your graph might look slightly different than your classmates or slightly different than mine. The important points, though, that I have to see to give you credit, as long as your local max had an input of -3 somewhere along that line, and as long as your local min was lower than it and it was on the input 1, you're just guessing the heights of those local mins and maxes, you'll get credit. And as long as your inflection point was somewhere on this orange line, where the input being a -1, and it's in between the min and the max, you'll get credit. Okay, any other questions on this one? There's one more example in the notes that we're not going to have time to do, so I'll post a video because I want to finish these notes. We are going to be done with these notes, so you can't do it over the weekend. And then I'll get us caught up next class because if you've looked at the 4.5 notes, it's so short. 4.5 is like, you don't really need it. You can just do sign charts, but I will cover it. So I'm going to do a video for this one. So put a little note here, see video. Okay. It's the same idea, but this time if your derivative, see how the derivative is a cubic function? If you work back to your original function, what degree would you expect it to have? Yeah, to the fourth, right? So you would expect, since you're going to do a possible graph of f of x, you would have something, you know, maybe that looks like this or this. We don't know, but it's the same kind of idea. And I'll post a separate video for that, okay? Because we need to talk about points of diminishing returns, and I think we can do it in 4 minutes. Because there's no graphing on this. It's just an application of second derivatives. Are you ready? So here's the idea of point of diminishing returns. Okay, we're going to read this example up here just to kind of get an idea of this business concept. It's basically just analyzing a second derivative, right? But this is what's happening. It says, if a company decides to increase spending on advertising, it would expect its sales to increase, right? If you're pouring more and more money into advertising, you're only doing it because you expect to sell more stuff. That's the point of advertising. So at first, when you first start advertising, your sales will increase at an increasing rate. You're going to get more and more people coming in faster and faster, right? Because it's new and exciting and they're seeing this advertisement. But then after a while, you're still going to get more people in, but not as quick, like it's slowing down a little bit. And that sweet spot, that point where your rate of change of sales is increasing faster and faster, and then it starts to taper off, that's called the point of diminishing returns. The point of diminishing returns is when you're making a decision, is it worth my investment? Do I want to put more money, in this case, into advertising? Am I going to get the biggest, bang, the biggest return on my buck here or not? It's finding that sweet spot. And since it's telling us how our rate of change of sales, at first sales are going to increase at an increasing rate. See how you're seeing increasing? It's how your rate of change is changing. That's a second derivative. So this is just an application of second derivatives. That's all it is. So it says the point of diminishing returns is the point where the rate of change has a maximum value. That means money spent after this point, it might still increase your sales, but at a lower rate. So it might not be advantageous for the company to invest more money, right? We're trying to find that sweet spot. So let's see this in an example. Again, there's no graphing here. It says currently, a discount appliance store is selling 200 large screen televisions monthly. If the store invests X $1,000 on an advertising campaign, it estimates that sale will increase to this amount. So basically, remember, whenever you're given a function, ask yourself, what's your input and what's your output, right? So that's what I'm going to do here. Okay, my input X is thousands of dollars that they're investing. So X is representing money invested in thousands. And the output that we're calculating is sales. This is calculating the sales that come out. And I want to know, how are those sales changing? Are they increasing? Are they decreasing? This is going to calculate sales of large screen TVs. And it's only, my input is only going to work between, they're only willing to invest between $0 and $9,000. That's what that domain is telling us, right? We're going to invest between $0 and $9,000. So I'm going to write that out. So $0 and technically this means $9,000. And this is money invested. So always understand your function before you try to work with it. And it wants to know, when is the rate of change of sales increasing and decreasing, and what is the point of diminishing returns? So that's what I'm going to jump to real quick. Point of diminishing returns. The point of diminishing returns is this. Here's your definition. The point of diminishing returns happens when the second derivative changes from concave down to concave up. I said that backwards. From concave up to concave down. And I know we're out of class time, so what I'm going to do real quick is graph this function and just show it to you And then unfortunately, y'all, I'm going to have to do a video for y'all. But if I show you on the graph, y'all know how to do a second derivative sine chart. So it's just creating a second derivative sine chart and seeing where this changes. So let me show you why it's concave up to concave down. So concave up to concave down. You want to know this point where I go from concave up and then I switch over to concave down. So the reason why that is your rate of change of sales, right? If this is a graph of sales, see how your sales continue to go up no matter what. You're going to, if you're pouring more money into advertising, you're going to expect your sales to go up. But at first, when you first start your advertising campaign, see how the rate of change is kind of flat, but then the rate of change starts shooting up, and the tangent lines get higher and higher and higher. But at this point, the tangent lines start to taper off again. So the tangent lines are the first derivative of the function. Sales are the actual function, right? Sales are the function. The tangent lines are the first derivative, and they're starting to taper off. And that point where my tangent lines are the steepest, that's where your second derivative is going to hit 0. And it's going to be concave up before that point and concave down after that point. So in the video, what you're going to see is I'm just going to take your first derivative. I'm going to take the first derivative. I'm going to find the second derivative. I'm going to create a sine chart for this. And then wherever the sine chart goes from concave up to concave down, that's my point of diminishing returns. And there's not a lot of interpreting or anything you have to do. Just be careful reading your units for the input and output. Okay, I know some of y'all have another class to go to, so you need to go write yourself a little note to see the video. I'll make a separate video for this one, but I promise it's not hard. You know how to do a second derivative sine chart. The only thing you're having to memorize is what the point of diminishing returns is, and it's this definition right here. Okay? Okay, you have a lot of work to do this weekend. On Tuesday, we're going to get caught up. Okay, we'll do section 4.5 on Tuesday, and we'll start our word problems, which are scheduled for 2 days. So I'm going to move the 4.5 homework due date for you guys. I'm putting that on my to-do list. Okay, so feel free to log off. I'll hang around if you have questions. Thank you for your patience today.
Hey, Kelly, how's your son?
Oh, he's good. His fever's gone. He still has a cough, but I was nervous. So luckily, negative COVID test. How are you doing, Arjana?
Good. I'm doing a lot better. Yesterday was rough, but I'm doing a lot better today. Yeah, I was worried about him because I spoke to a doctor and he said that the flu's going around pretty bad. So
yeah,
I hear he's okay.
Thank you. Yeah, luckily we got our flu shots a while back, but yeah, thank you for asking.
Oh, of course. All right. Have a good weekend. Thank you.
You too. Oh, and guys, if you're still on here, vote this weekend. Go vote. I just got done teaching the mathematics of voting in my night class, so make sure you go vote. Who here, has anyone in the room voted?
Yes, I voted. Also, guys, if you go vote, there's a whole list of free things you get for voting. You don't have to prove. All you need is your voting sticker. And there's a whole list on When, What, Where, Austin that you can get so much free food, free alcohol, free drinks, free nails, like so much free stuff. Go vote.
That's awesome. I'll let my students know. Cool.
Yeah, it was really cool. My fiance and I last week, whenever we went to go, but that's when I think I got sick. Is whenever I went to go.
Oh no.
And after that, we drove around and we went to go pick up just like a free item from everywhere. Like we got free tacos, we got free. What else did we get free? We got free beers, free ciders, we got free pizza.
That's awesome.
Dumplings. Yeah, it was really cool. When, What, Where on Austin, on their Instagram page, When, What, Where Austin has like 3 pages full of free things in Austin that you get.
That's awesome. I'm gonna post that as a Blackboard announcement. That's cool.
You should, yeah. All right, I can send you the link to it if you want.
Yeah, I can Google it. I wrote it down. When, Where, What, Austin.
When, What, Where Austin. Yeah.
Oh, When, What, Where, Austin. Okay, cool. Awesome. Have a great weekend. Oh, look, Renee, you're so on top of it. That is awesome. Thank you. Bye. Thank you, Renee.